All right, example 2. A weight loss boot camp is trying out 3 different exercise programs to help their clients shed some extra pounds. All participants are assigned to a team of 4 people, and each week their entire team is weighed together to see how many pounds they were able to take off. The data shows their weekly weight loss as a team. Were the exercise programs all equally effective in helping them lose weight? Note that all teams tried all 3 exercise regimes, but they all received the treatments in a random order, right? So this is definitely a case where we have 3 different treatments, treatment 1, 2, and 3. And we have data points, which are going to be pounds lost, I think. How many pounds they were able to take off per week, pounds lost per week. But these are not independent samples. They're actually linked to each other. What's the link? It's the team of 4 that lost that weight, right? So this team lost that much under this exercise regime, lost that much under this exercise regime, lost that much under this exercise regime. Now, each team got these 3 exercise regimes in a different order. Some people got 3, 2, 1, some people got 1, 2, 3, some people got 2, 3, 1, right? So they've all been balanced in that way. All right, so if you pull up your examples and go to example 2, you'll see this data set. So here are the different teams or squads. Here are the 3 different types of exercise programs, and here are the different orders that they were that they did these exercises in. And each exercise was done for a week, right? Okay, so let's think about this. So to begin with, we need a hypothesis. So step 1 is the null hypothesis. And all mu e's are equal, right? So all the mu e's, exercise 1, exercise 2, exercise 3, they're all equal. The alternative hypothesis is that not all mu e's are equal. All right, so step 2. So step 2 is our significance level. We could just set alpha equals to 0.05. Once again, because it's an omnibus hypothesis, we know we're going to do a F-test. So it doesn't need to be two-tailed, right? So step 3, this is the decision stage. If you sort of imagine that F distribution in your head, sort of color in that part, what is that F, critical F? Well, in order to find the critical F, we're going to need to find the DF between as well as the DF residual, right? Because that's the numerator and the denominator degrees of freedom. In order to find DF residual, though, we're going to also need to find DF subject. And remember here, subject doesn't mean each individual person. Subject really means case. And each case here is a squad, right? So how many squads are there? -1. So count how many squads there are, -1. Oops. Oh, it's not counting them because they're not numbers. I'll just use this column instead. Doesn't matter. So there's 11 degrees of freedom for subject. For degrees of freedom between, what we're going to need is the number of different samples, which is 3, so K, -1, right? So 3 minus 1 is 2. I'll just put that in. And so my DF residual is the DF between times the DF subject, and that's 22. So let's find the critical F. We need F inverse. The probability that we need is 0.05. The degrees of freedom for the numerator is 2. The degrees of freedom for the denominator is 22. And our critical F is 3.44. All right, step 4. So in step 4, this is probably going to be our most complicated step. Here we're going to need the F statistic. And in order to find F, we need the variance between divided by the variance residual. In order to find variance between, we're going to need the SS between divided by DF between. We already have DF between, thankfully, so we do need SS between. And the concept of SS between is the whole idea of each sample's x bar, their distance away from the grand mean, squared. And then depending on how many subjects you had in your sample, how many data points you had in your sample, you get weighted more or less. Now, the nice thing is all of these have the same number of subjects, right? But let's go ahead and try to do this. So first we need the different samples. So it's exercise 1, exercise 2, and exercise 3. We need their n's. Their n is going to be 12, right? There's 12 data points in each sample. We also need their each exercise regime's average weight loss, right? So we need x bar. And we also need the grand mean, because ultimately we're going to look for n times x bar minus the grand mean squared. And then we're going to add all of those up. So let's find the x bars for exercise regime number 1. So that and Excel makes it nice and easy for us to just find out all those averages very quickly. And then once we have that, now we could find the grand mean. The grand mean is also very easy to find here. We just want to select all the data points. Oh, I think I've selected one of them twice. Be careful about that. Okay, so make sure everybody is selected just one time. So this is the average weight loss per week, regardless of which team you were on, regardless of which exercise you did. All right, and now let's find n times the x bar minus the grand mean squared. And let's do that for each exercise regime. Once we have that done, we could find the sum. And the sum is 23.63. So here in SS between, I would put that number there. Great. So once we have that, now we could actually find this because we already have calculated the DF between. Wasn't too hard. All right. Now we have to work on variance residual. Now in order to find variance residual, let me just add in a couple of rows here. Actually, let's just cut and paste this down here. Nothing has changed. Excellent. Okay, just to give me a little more space, variance residual. In order to find variance residual, I'm going to need to find SS residual divided by DF residual. We already have DF residual, so we just need to find SS residual. In order to find that, I need SS total minus SS between plus SS subject level. So I already have my SS between, so I need to find SS total and SS for each subject. All right, so let's get at it. So SS total is going to be for every single exercise regime, for every single one of these data points, I need to find that distance away from the grand mean, add them all up, square them, add them all up, and that's going to be my SS total, right? So for E1, here's my subtotal for SS total. For E2, my subtotal for SS total. And for E3, my subtotal for SS total. So that's X minus the grand mean, and I'm going to lock that grand mean down, squared And I'm going to make sure I do that for every single data point in E1. So if I check on that, it's that last data point. And then I'm just going to go ahead and copy and paste that all the way up to here. Let's just check on this one. This is taking this value, subtracting it from the subtracting the grand mean from it, and then squaring that distance. All right. So once I have this, I could sum them all up and get my SS total. My total sum of squared distances. So I'm just going to put a pointer here so that I don't have to rewrite the number. And once I have that, all I have to find is SS subject. Now remember, SS subject, each subject has its own little mean because they've repeatedly been measured, right? So we have to find the subject's means, and then we have to get the distance between their means and the grand mean, square that, and multiply it by the number of measures, k. All right, so let's do that here. First, we need to find the subject's x bars, right? So that's going to be each squad's average weight loss. So some squads probably lost more weight than others. Okay. So this is the average weight loss for each squad. So it looks like, this squad lost quite a bit, whereas, 9.5 pounds, not too shabby, but still maybe a little bit different, right? So a little bit of variation in subject success. And here we're going to look at K times the subject's x bar minus the grand mean squared. So we already know K. K is going to be 3 times the subject's x bar minus the grand mean. I'm just going to use the one we've already calculated down here. And, of course, lock that down so I could copy and paste this. Squared. So, copy and paste that all the way down. And I could find the sum right here. And this is going to be my sum of squares for subject. It's a sum of a bunch of squares. All right, so that's 34 something. And I'm just going to put a pointer there so I don't have to retype that. But I could just see it nice and clearly right here. Okay, so now I have everything I need in order to find SS residual. So I need SS total minus my sum of squares between plus sum of squares subject. All right, once I have that, now I could find my residual variance divided by degrees of freedom. Okay, so here it looks like my residual sum of my residual variance is much smaller than my between sample variance, right? And so I predict my F value will be pretty big. So 11 point something divided by 2 point something. And that gives me 5.219. And that is a little bit bigger than my critical F, right? So if I find my p-value, F dist, and put in my F, my numerator degrees of freedom, my denominator degrees of freedom, I would find 0.01 something something, right? So that seems like a pretty small p, smaller than 0.05. So I'm going to be rejecting my null. So let's put step 5 down here. Reject the null. And we know that once you reject the null, you're going to need to also do post hoc tests as well as find eta squared. All right. So that brings us to example 3. What is the problem with a bunch of tiny t-tests? Well, with so many t-tests, we might get confused. No, it's not a good answer. With so many t-tests, the probability of type 1 error increases because we're increasing the cutoff A. Actually, we're not increasing the cutoff A. We're keeping A at 0.05, but the type 1 error increases because we have the possibility of rejecting the null multiple times. With so many t-tests, the probability of type 1 error increases, here it is, because we may be rejecting more null hypotheses. This is actually a correct answer, but this is a choose all that apply problem, so we might not be done yet. With so many paired samples t-tests, we have a better estimate of S because we're estimating S several times. That's very hopeful, but mathematically untrue. With so many paired samples t-tests, we have a poorer estimate of S because we're not using all of the data to estimate one S. In fact, we're just using subsets of the data to estimate S several times. That's a good answer.